an exponential function is of the form b to the x, where b is a number larger than 1. X is our variable. Notice the x is in the exponent and a number is in the base. We call this an exponential function. The graph of an exponential function looks like this. In the positive direction, it grows pretty fast. In the negative direction, it approaches 0, but it always stays above the x-axis. And of course, for b, any number larger than 1, in fact, for b, any number but 0, b to the 0 is 1. So exponential functions will always go through 0, 1. Now, you'll notice with this, exponential functions satisfy the horizontal line test. So the inverse exists. So let's draw a graph of the inverse and then talk about why the inverse existing is useful. So let's first draw it by drawing the line y equals x. I always draw it as a dotted line when I'm drawing it, just so I have a frame of reference. This point, instead of being at 0, 1, is going to be over here at 1, 0. I'll label that down there. The rest of it will look like this. So this piece will turn into that. This piece will turn down like that. And right there we have the inverse of an exponential function. Actually, I'm going to call this a y equals b to the x, because down here I also use y. I could use f and f inverse. I'm just going to use y for this. So this right here, this is the inverse function for the exponential functions. We have a special name for that given base b. Y equals log of x with base b. Log is short for logarithm. So logarithm of x with base b, given exponential function b to the x. So right here, log of x with base b gives us an inverse for an exponential function. Now, why is that useful? Well, in general, why are inverse functions useful? Inverse functions are useful because they allow us to solve functions for x. Well, among many other things, they allow us to solve some functions for x. So let's look at let's look at one example using this, but let's look at two examples. Solve for x. Two to the x equals 5, first example. Two times x equals 5, second example. And let's do the second example first. Second example arguably is easier than the first one. How do you solve 2x equals 5 for x? Well, you look at the x, you see the x there, you think, that 2 is in the way. If I want to solve for x, I need to get rid of that 2. How can I get rid of that 2? Well, we can invert it. 2 and 1/2 cancel out and make 1. 2 and 1/2 are what is known as multiplicative inverses, because you multiply them together and they make 1. We can use a multiplicative inverse to solve this for x. Multiply that side by 1/2, you get x. Multiply this side by 1/2, you get 5/2. 2 can be inverted. A very important piece of language that I would imagine none of you used to solve this when I first said it. But it's very useful to think in terms of inverting numbers. I mean, you could say divide by 2. You could say, multiply by the reciprocal. But using the language of inverses allows you to think of that equation and this equation in very similar ways. Now here, we can't divide by 2 and get rid of that 2, because the x is in the exponent. But what we can do is invert that function. What does that mean? Well, it means we use the property of inverses. So right here, what do we have? We have a half and 2 kind of canceling out, well, canceling out and making a 1. What was the definition of an inverse function? An inverse function said you could use composition and be left with just x. You could use composition in this direction or the other direction and get just x. And that's what we want to do here. We want on the left side to be left with just x, because our directions say solve for x. And how are we going to do that? Well, I'm going to erase this lower equation because I might need that space. And I'll say we invert the exponential. How do we do that? Well, here's the inverse of an exponential. Take a logarithm. Let's spell logarithm correctly. Let's try to spell it correctly the third time. Logarithm. Take a logarithm with base 2 of both sides. Take a logarithm with base 2 of both sides. Well, what do you get on the left? Well, what does that even look like? Well, let's write it like this. Log with base 2. This is imprecise notation, but it's okay. We have the equation 2 to the x equals 5. Let's take the logarithm with base 2 on both sides. Well, what happens on the left side? Logarithm and exponential cancel each other out. Inverse functions cancel each other out. Just like inverse numbers cancel each other out. So on the left side, logarithm of 2 to the x with base 2 is just x. And on the other side, logarithm of 5 with base 2 is just log of 5 with base 2. And you don't have to simplify that. I mean, the right side really can't be simplified. So here, we used a logarithm to solve for x. It's very important. It's very, very important. Also important are some exponential and logarithm rules. We have 3 exponential properties. These are just numbers, a, b, c, and x. A to the b times a to the c is a to the b plus c. A to the b raised to the c is a to the b times c. A to a negative number is 1 over a to that number. There are many ways you can think of them. I like to think of them, well, remember, an exponent just counts how many things you have. So, like, x to the 5th is x, 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 x. In other words, x to the 5th is 5 x's, all multiplied together. If you have x to the 5th, and then you have x to the 3rd, well, what do you have? You have x to the 5th, x to the 3rd. You have 5 x's and 3 x's. So you have 8 x's. 5 plus 3. And similarly here, if you have x to the 5th, x to the 5th, x to the 5th, meaning 3 copies of x to the 5th, you have 5 x's here, 5 x's here, 5 x's here, 3 copies of 5 copies of x, giving you 3 times 5 copies. So you could memorize them. I like to think of these in terms of counting just about every time I see them. Every time I see these, I think back to an example just like that x to the 5th, x to the 3rd. But those are exponential properties, and logarithms are just the inverse functions of exponentials, so they have parallel logarithm properties. Log, notice in all these the base doesn't matter, so it's just b. Meaning these work for any base, any allowable base. Log of a product, log of x times y, splits into log of x plus log of y, preserving the base. Log of a quotient, x over y, splits into log of the top minus log of the bottom, preserving the base. Log of something raised to a number, that number can come out with multiplication. So log of x to something is that thing times log of x, again preserving base b. This middle property is actually just a combination of these two properties with that observation. So I sometimes don't even include this in the list, but I did today. So we'll use these properties a few times. Let's use them just for this example. Where's my eraser? Yeah, that might have looked strange. I looked over there for an eraser. My living room chair is over there, and I frequently put the eraser on the back of the chair because of how much I knock it over when it's here. But I left it there that time. Solve for x. What do we have? Log, let's use base 10 with root x, log of root x with base 10, plus log with base 10 of x equals 2. So solve this for x. We'll use those properties. We'll use those properties. There are, right off the bat, two different things you can do. I will do one of them. You could use property 1 and combine those two things on the left and get log of x to the 3/2 with base 10. I won't do that. And then solve, take a 10 to both sides, then whatever the number is. I won't do that. I'm going to use property 3 first. Because root x, remember, is just x to the half. So all I did, write that as x to the 1/2. Then you can bring that half out front, as I have here. Well, now we can solve this in a couple steps. If you have half of something, and then you have 1 of something, you have 1.5 of that thing. 1.5, also known as 3/2. So on the left side, we have 3/2 of a log of x with base 10 equals on the other side 2 still. Well, what can we do with this? Well, let's get rid of that 3/2. Multiply everything by 2/3. 2 times 2/3 is 4/3. And now all we have is a logarithm of x with base 10. We know how to invert logarithms because exponentials invert logarithms just like logarithms invert exponentials. So take 10 to the left side, you get x. Take 10 to the right side, you get 10 to the 4/3. And 10 to the 4/3 doesn't conveniently simplify, so you don't have to simplify that. So what we did was raise 10 to both sides to solve that last equation. And we used logarithm properties to help us out. If you used the other logarithm property first, you'd get what? Log of x to the 3/2 with base 10. Then you could bring the 3/2 out front, you'd get this equation. And then you'd solve the same way after that. But let's make one last remark about logarithms. Remark. There is an important number. Number called E, which is approximately equal to 2.718, that's all I wrote here, equal to something like that. It's a very important number in calculus, in physics, probably chemistry, I don't know. I should probably know that. But it's very important in calculus, which is what we're taking. And with this number, so I'll say and log of x with base e, if the base of the logarithm is this number, which we do abbreviate e, we write this as ln of x. So ln of x, it's assumed to mean a logarithm with base e. And ln of x is called the natural logarithm, because e is known as a natural number. E is known as the natural exponential, I should say. Natural number is very different. E is the natural exponential, and we'll actually see one of the reasons that it is in calculus. Those of you who may have seen calculus, the derivative of e to the x is itself. So where was I? We'll see that at the end of week 2. And log e is written ln x, and ln x is called the natural logarithm of x. The quotes should be over there. Natural logarithm of x. And let's just look at one example of solving for x with this. Solve for x. Natural log 1 over x equals 4. How would we solve this for x? Well, you could make an exponent observation, like this is x to the -1, bring out the negative and then solve. I won't do that. With all logarithms, there are multiple ways to solve. I'm going to immediately take an exponential of both sides. To invert a natural logarithm, logarithm of base e, we take e to both sides. So e to the left side is 1 over x. E to the right side is e to the 4. No need for simplification. Now we need to solve this for x. Well, a couple ways you could do that. Multiply by e, divide by e to the 4th, or you could just flip both sides around. So flip both sides around. X is 1 over e to the 4th, or e to the -4th. I'll just leave it like that. You could write that as e to the -4th. I'm generally fine with negative exponents. So all of these preliminaries will show up in this semester at some point. They're all very useful. So try the problems on the worksheet with these and see how they go.